This is my chapter summary for Matter and Interactions, 4th edition, Chapter 6, the energy principle. It's a big deal. It's a big summary. It's a big chapter. Big. Before we get into that, let's just pause for a second. I mean, if you think about what we've really done so far, it hasn't been that much. I know it's 5 chapters. But the most important idea is this. This is what we're dealing with right so far. F net is, you could write it as a derivative or a change. Let's write it as delta P, delta T. It's the change in momentum. The net force on an object is a change in momentum. And if you write that as a derivative, it would be dP, dt. And then, so we really did 2 things with that. Number 1, we had special forces, like the gravitational force is mg, or the real gravitational force is negative g m1 m2 over r squared r hat, or the force due to a spring is negative k s l hat. We did all these forces, and if you know the force, you can say something about the change of momentum. Or we knew something about the change of momentum. I knew that dp dt was 0, and so that meant the net force was 0. Or the magnitude of dp dt was mv squared over r, and that would be the case for something moving in a circle. So that's all we've done so far. Really, that's what we've done. And there's a lot of little details, but that's fine. So now we want to start with energy. It's a new idea, and there's a lot of stuff here. Okay. So first, let's define the energy of a particle. So if I have a single particle like this, moving with some velocity v and a mass m, I can define the energy of that particle as gamma mc squared. Okay, so we're going to start off with some big ideas that don't always get implemented in a lot of everyday stuff. But this is a big idea. Remember this gamma, we saw that before in our definition of momentum. We had momentum was gamma mv, and in both these cases, gamma is 1 over the square root of 1 minus v squared over c squared, where c is 3 times 10 to the 8th meters per second. It's the speed of light. So the energy of a particle, then you could write it as this, mc squared over the square root of 1 minus v squared over c squared. And that's the magnitude of the velocity right there. Now, it turns out that what if I have a particle at rest? And this is kind of a big deal, right? This says that if v equals 0, then E, we'll call this the rest energy, is equal to mc squared, but v is 0, so I get 1 minus 0, square root of 1 is 1, so let's get mc squared. So we call this the rest energy, mc squared. And with that, I can actually write the energy of any particle as E equals mc squared, the rest energy, plus some other term, and we call that other term the kinetic energy. Now, if the particle is moving very fast, if it's moving near the speed of light, so you can't ignore this term, then it's not easy to write the kinetic energy as a separate term. Okay, but K is what we call the kinetic energy. It's the energy, so you can break this into 2 parts. Energy depends on its mass, mc squared. That's that E equals mc squared, right? You've seen that before, very famous equation. Plus the energy due to its motion. And it is a very important idea, even though I'm not going to emphasize that in my class for a lot of problems, but we will talk about it. So that's that. Now I want to switch over to low speeds. And by low, meaning v is much less than c. So let's say low speed. V much less than c. So that's a c. And those are less thans. So, like the fastest plane ever flown by humans, or a speeding bullet, or things like that. Low speeds, right, compared to c. In that case, we can approximate the kinetic energy as 1/2 m, and I'll write this the long way, v squared. So you take the velocity of the particle and you take the magnitude, you square it, multiply 1/2, and that's the kinetic energy. And so let's just jump into, I'm trying to think here. Let's just jump into the work energy principle, right? Because we talk about energy, but who cares about energy? And the answer is work energy is the reason that we do that. And this is a big chapter, okay? And there's some big ideas. So it's kind of hard just to jump into this. We're going to do it anyway. So the work energy principle says that work done on a system is equal to the change in energy of the system. So if I just have a particle, I would just have kinetic energy. I'm not going to worry about the mass energy right now. But what is work? How do we define work? Well, work is defined as for a constant force, F dot delta R. So we've seen F before as a vector, and we've seen displacement as a vector. And so here you have a new operation that was actually covered in the previous chapter, but I didn't talk about it. And it's called, how do you operate two vectors together? I can't multiply them together. This is called the dot product, also known as a scalar product. So let's just talk about mathematically dot products for a second, because they're important. So suppose I have a vector A, and I'm going to write that as AX, AY, AZ. And then I have a vector B, which is BX, BY, BZ. So it has X, Y, and Z components. And, I could add those two vectors. I could subtract those two vectors. I could multiply by a scalar. I could find unit vectors. We've done all that before. But we define A dot B as the product of these two vectors, scalar product. It gives us a scalar value. So we do this. To do this, we take the x component of A, multiply it by the x component of B. AX times BX. And then we add the y component of A multiplied by the y component of Z. And then we add the z component of A times the z component of Z. So each component is a scalar value. So when I multiply AX, BX, I get a scalar. So that's a scalar, that's a scalar, that's a scalar. And if I add three scalars, I still get a scalar. So the dot product A dot B gives us a scalar value. We can think of this as the projection of one vector onto another. So here's A, here's B, and how much of A is pointing in the direction of B, and multiply them together. So this is my projection. And you can see that if I know the angle between those two vectors, I could find that side right there. So you can actually write A dot B as the magnitude of A times the magnitude of B times the cosine of the angle between them. So we actually have two definitions for the dot product. So if you know the angle and the magnitude, you can use this one. If you only know them in component form, you can use this one. So with that, we get the following definition for work, which I already wrote, F dot delta R. Okay, I think what I want to do is go ahead and do an example. I want to show you how to use the work energy principle for something that we could do without the work energy principle. So we could do it two ways. I think this will be the best introduction. So imagine that I have ground, and I have a ball, and it starts at a height of y1, and it falls down here to y equals 0. So the final y is 0. So it's right there, right before it hits. Let's use the momentum principle to find out how fast it's going. So if I know that I have the gravitational force acting on this. So I can write F net equals delta P over delta T. And in this case, I only have to deal with the y direction. So I could write this net force in the y direction as negative mg. And that's going to be equal to P2 minus P1 over delta T. Now, we can do little tricks here, and I don't know how much we want to go into this. I don't really want to go into it too much. So I'm going to go ahead and use, since I've already solved this problem before. The problem here is how fast is it going down here? I'll call that V2, the magnitude of that. And V1 is 0. The problem is that I don't actually know the time it takes, and this depends on the time. So let's write this as m v2 minus v1. Those are scalar values over delta t. And let's say that if I know v1 is 0 and v2 I don't know, I can say delta y over delta t, that's the average velocity, is going to be v2 plus v1 over 2. And v1 is 0. So delta t, I really want delta t. Delta t is going to be equal to, if I just solve this, I get 2 delta y over v2, right? So if I multiply both sides by delta t and divide by v2 and multiply by that, so I get that. Now I can put that in over here, and I get these masses cancel. I get negative g equals v2 minus 0, v1 was 0, divided by this, 2 delta y v2, I got the v2 up top, so I get negative 2g delta y, multiply both sides by delta t. I know this looks dumb, but just trust me, equals v2 squared. Delta y is actually negative, right? It's going to be equal to the final y of 0 minus y1. So this is going to be 2gy1 equals v2 squared. So v2 is going to be the square root of 2gy1. So that's how fast it's going when it hits the ground, right before it hits the ground. Now let's do this with the work energy principle. So the first thing I'm going to do, and we'll talk about this in a second, is I'm going to say the system of just the ball. And I'm going to say the work is F dot delta R. So I need to calc, and that's going to be equal to the change in kinetic energy. So what's the work done on the ball by this force as it moves down? So let's write this as a vector. Fg is going to be equal to 0, negative mg, 0. That's the gravitational force. Delta R is going to be 0, and this is going to be y2, final minus initial, that's y2, minus y1, 0. So now I can do the dot product, Fg dot delta R, and that's going to be 0 times 0 plus negative mg times negative y, so I get plus mg y1, plus 0 times 0. So the work done on this by gravity is equal to mgy1. And that's going to be equal to the change in kinetic energy, which is 1/2 mv2 squared, that's the final kinetic energy, minus 1/2 mv1 squared, that's the initial kinetic energy. But I said this starts at rest, so we're just doing a simple problem. So now I have the following. I have this is equal to that. I want to try to fit on this one piece of paper. mgy1 is 1/2 mv2 squared. Mass cancels. Multiply by 2. Take the square root. v2 is the square root of 2gy1. So this is just an example, but you see we get the same answer either way. Okay, so the work energy principle is a different way of looking at things, and that's the important thing right there. Now, and we're going to talk about why you would do work energy at the end, but I want to talk about this value of work, because here we did work as positive. Let's imagine I have some balls, and I'm just doing work done by gravity. So we already did this. If the ball is going down, delta R is that way, and the gravitational force is down. So in that case, oops, I'm sorry, can't see. So in this case, case 1, work done by gravity equals a positive number. All right, we already did that. It was positive. So you can think of this too, because this is going to be equal to F, that's a G, G delta R cosine theta. In this case, theta is the angle between FG and delta R, and that's 0. And the cosine of 0 is 1. So this would be positive work. And this means that increase in energy of the system. Or delta E equals positive also. Okay, what about another case? What if I have a ball, but I throw the ball and it's going up? So it's going from 1 to 2. Now, delta R is this way, but the gravitational force is that way. So work will be equal to a negative number. And again, you could think of this as equal to Fg delta R cosine of pi, right? Because the angle between the gravitational force and displacement is 180 degrees pi, and the cosine of pi is -1. So we get negative work. And this means delta E is negative also. So the energy is going to decrease, which makes sense. As this is moving up, the ball is going to slow down, so the final kinetic energy is going to be less than the initial kinetic energy. Here's another situation. Suppose I have a ball and I'm carrying it. So here's my hand. Trying to draw. Here's my hand. And I'm moving it this way, delta R. And I just want to consider the work done by gravity. So gravity in this case would be down. So work would be equal to 0 because that's Fg delta R cosine of pi over 2. The angle between those two is pi over 2, and the cosine of pi over 2 is 0. So there's no work done when the two things are perpendicular. So in general, if I have delta R and F, even if it's at some angle less than pi over 2, then it's going to do positive work. If it's perpendicular, it's going to do 0 work. And if the angle is greater than pi over 2, it's going to do negative work. So backwards pulling force, forwards pulling force, perpendicular force. So work can be positive, negative, 0. I never even said what the units for energy were. So energy, we use the units of a joule, where 1 joule is 1 kilogram meter per second squared. Meter squared per second squared, sorry. Okay, that's the units of joules. And just as a feeling, the one thing I like to do, if you take a textbook and you take it from the floor and you put it up on the table, that's about 10 joules. It's about 10 joules of energy to take a textbook and put it on the table, just as a rough estimate. Okay, I put my notes over here. I gotta look at my next page because I told you this is a big chapter. Okay, what about work done by a non-constant force? And work can be more complicated, right? So far I did Fg equals a constant, C, whatever. I also did delta R is equal to a constant. And so the dot product of two constant vectors is easy. But what if the delta R changes or the force changes? So imagine I'm going along some crazy path like this. So I want to go from point 1 to point 2, and I want to calculate the work, and the force changes. So maybe right here, the force is this way, and then over here, the force is that way. And then here, the force is this way, and so forth. So it changes. Well, how would I calculate the work? Well, I could do the following. I could break this into steps of delta R and calculate the work for that step. And then I could do another step of delta R, and then another step of delta R. And then for each of those steps, I could calculate the little bit of work such that the total work would be the sum of all these steps of F dot delta R. So I'd have to add up a bunch of tiny little works where I'm assuming the force is constant over those steps. And then I could calculate the total work. It turns out, though, also I could do this. If I'd let delta R go to dr as an infinitesimal step, then this sum of an infinitesimal steps becomes an integral. So I get work is the integral from point 1 to point 2 of F dot dr. Now, this looks simple, but it's not. Put a note here. Not simple. Because what if I want to do F dot dr going from point 1 to point 2, and I go this way? That's not so bad. What if I do this? How do I accommodate that path in this integral? So this is technically a path integral or a line integral. And we're only going to do simple ones here, but I just want you to know that that can be very complicated. So we're only going to do that in mostly simple cases. But this is how I can calculate the work for any force, even if it's not constant. Also, if the path is not constant. So let's do this for a situation. Let's calculate the work for a non-constant force. So one of the non-constant forces we have is the work done by a spring, or the force from a spring. So let's make this simple though. So here's my wall, and here's a spring and a mass. I don't really care about the mass. And let's call this x equals 0 just to make things simple. And if I stretch it over here a distance, that's a distance x, then there's going to be a force pulling back in the x direction. I can write that as an x component, fx, is negative kx. In this case, because I put x equals 0. Remember, we really said the spring force is negative k s L hat. And that's a better vector form of that, and where s is the stretch. But here I'm making x the stretch, just so we can do an integral. Now we can calculate the integral going from 1 to 2. The work done is going to be the integral from 1 to 2 of the force, negative kx. And dr in this case is in the x direction, so that's just going to be dx. And this is an integral that we can do because negative k is a constant. I can bring that up front. Negative k. Let's go from x equals 0 to x equals s, some stretch. Negative k from 0 to s, x dx. I can integrate that. It's the antiderivative. So what would I take the derivative of and get x? And the answer is x squared over 2. So I get work equals negative 1/2 k s squared from 0, x squared from 0 to x, 0 to s. And that's going to be negative 1/2 k s squared minus 0, negative 1/2 k s squared. So the work done by the spring is a negative value, right? Because I'm pulling this way, but the spring's pulling in the opposite direction as the way we're moving, so we get a negative work done. But that's how I'd calculate the work for non-constant force. Let's jump over here, just looking at my notes, to another case. And I'm just throwing this in here because it's kind of cool. Suppose I have a particle like a neutron. And it turns out if you have a neutron by itself, even though we think of these all over the place, and they are, right? And in fact, everything that you look at is probably either made of just 3 things: neutrons, protons, and electrons. But a neutron has 0 net charge, but it's not stable. And in fact, it can decay into 3 particles: a proton, an electron, and a neutrino, which is that's a bar, a neutral tiny particle. Suppose I want to find the rest energy of the neutron. So E equals mc squared. Well, the mass of a neutron is super tiny. It's 1.6749 times 10 to the negative 27th kilograms, and c is 3 times 10 to the 8th meters per second squared. So the energy of a neutron, mc squared, is equal to 1.51 times 10 to the negative 10 joules. Well, that's a terrible number to deal with. So in fact, we come up with a new system that you will understand when you take the second semester, an electron volt. And it sounds cool too. Electron volt it's technically the energy one electron gets by going through 1 volt of electric potential difference. And we use EV for that unit, 1 EV, and it is equal to 1.6 times 10 to the negative 19th joules. So with that, and in fact we even do this, MeV is equal to 1,000,000 of those, so it's 1.6 times 10 to the negative 13th joules. So over here, the rest mass energy of a neutron is equal to 939.6 mega electron volts, or MeV. You can say it either way. You can say MeV, that's what most people say, or mega electron volts. Now, but here's the cool part. If I then find the mass energy, the rest mass energy of this stuff, so this decays into this, and I get the mass of that times c squared, the mass of that times c squared, the mass of that, I get 938.8 MeV. And this is one of the really weird and awesome things. You'll notice here that this mass is greater than this mass. So this decays and turns into 3 particles, but the mass is less than it was before. So how does that happen? Well, if this is my system and there's no work done on the system, then the total energy has to be the same. So if the mass energy decreased, then these all have to have kinetic energy. And I'm drawing that with arrows, they're not arrows. Okay. And so this decay process produces products with a lower mass, but they are also moving faster. And so you essentially transform some of the mass energy here into kinetic energy right there. And this is true for nuclear processes. You can get energy from the mass. It's kind of a big deal. This is how nuclear reactors work. It's also how they discovered the neutrino. So the neutrino, so neutrons are hard to find. They're hard to detect because they don't have any charge. A proton's positive and an electron's negative. And so you'll notice here, the total charge of the whole thing is still 0, so that's good. But these interact easily with matter because they're charged and they have an electric interaction. The neutrino is a very, very low mass neutral particle, and it's very difficult to detect. But what they did was they said, okay, here's my energy, here's my energy, mass energy, kinetic energy afterwards, and it doesn't all add up. So with that not all adding up, there had to be some missing piece because we know that that energy should be conserved. So it's one of the ways we find things. We look for cases where energy is not conserved, and then we make it conserved by looking for missing pieces. So that was a little aside. I'm just going by the order in the book. Okay, let's look at this one little bitty important thing, a relationship between momentum and energy. So if we have a simple system, we can define, we say work is the change in energy. And in one dimension, 1D, then we can say Fx times, let's write this. In 1D, F dot delta R is equal to Fx dx, delta x, right? Because if it only has an x component, the x component of this times the x component of that is that. And that's going to be equal to the change in energy. So that's the work energy principle for a single particle in one dimension. Now, what about a single particle with the momentum principle? Well, I have momentum principle is F net is equal to delta P delta T. But if I do that in one dimension, I get Fx equals delta P, that's equals Px delta T. So let's solve this for Fx. I get Fx equals delta E over delta X. And then these are both Fx. So I get delta E over delta X is equal to delta Px over delta T. So that's kind of a big deal. If I let the time and the distance go to 0, I get this as a derivative. The derivative of energy with respect to x is the derivative of the x momentum with respect to t. I mean, it's kind of a big deal for other things later. But I want to show you that this works if E is equal to 1/2 mv squared. And that's only for slow things, right? Then the total energy, I can just say, well, the total energy is actually plus mc squared, but that's a constant. So let's take the derivative of that with respect to x. dE dx is going to be equal to the derivative of this with respect to x. This does not depend on x, so that the derivative is 0. The derivative of this with respect to x is going to be 2 times 1/2 times m times v, right? I use the power rule to bring the 2 down front. But I have to also take the derivative of v with respect to x, the chain rule. So I get dv dx Okay, so now let's write this as the masses cancel. I get mv dv dx. And I'm going to write v as v equals dx dt in one dimension. So I get m dx dt dv dx. And here's one of those things that math people hate. I have a dx dx. Essentially, they cancel. They can. And I get m dv dt. If I bring the m in, I get dp. This is actually vx. dpx dt. So de dx is dp dt for slow motion. Okay, moving right along. That was in the book, and it's a good example. It's kind of cool. Let's see. We got a lot going on here, huh? A lot. Okay, we're getting close to the end. Let's consider another system. Let's suppose that I have the Earth and a ball, and the ball's falling down there. So let's consider the system of the ball. If I use the work energy principle, I can say work is the change in energy, change in kinetic energy, and I could calculate the work as F dot delta R, and we've done this, right? It's going to be equal to mg delta y. That's my change. That's my work done by gravity. No, negative. Wait. Negative. So F is that way. Well, delta y. Well, if y final is 0, that just becomes, that's fine. It is that way, right? mg. No, because mg is negative. Okay, let's write this out. So F is equal to 0, negative mg, 0, delta r is 0, delta y, 0. Yeah, so it's negative. Okay, negative mg delta y. And so we can say that the kinetic energy, delta y, could be negative, right? And the kinetic energy of the ball could increase or decrease depending on the value of delta y. We did that already. But what if I include the system of the ball plus the Earth? In that case, I have this as my whole system. There's no work done on the system. But I can now have change in kinetic energy of the ball plus change in kinetic energy of the Earth. But I know at the very least, one, the ball's going to increase in kinetic energy. The Earth, delta K Earth, is approximately equal to 0 because it's very, very massive, and we can do this problem later. So now I have this. I have a problem, right? I have 0 equals delta KB, but up here I know the change in kinetic energy is not 0. So how do I solve this problem? Well, the answer is that there has to be some other energy term in here. We have to have some other plus delta energy term. I'm going to call that delta U. And you can see here that up here I have this is delta K ball. So if that's delta K ball, negative mg, then delta U would have to be mg delta y. And we call this gravitational potential energy. We call this potential energy. Now, a couple of important points here. First, let me go ahead and say that that's for a constant gravitational field. In fact, we can calculate the potential for any force that is conservative, so not every force. I just lied. So I can really say delta U is equal to, if there's a force, negative 1 to 2 F dot dr. Why is there a negative sign there? Because in order to move it from a work to an energy, I moved it to the other side of the equation and it became negative. So this is how we define potential energy for a system. Now, if I have just there's two things I can do here. I can have the system of the ball and do work done by gravity, or I can have the system of the ball plus the Earth and have no work done by gravity because it's not an external force, but then I would have a change in potential energy. This is a change in potential. Okay, we will often write this as U equals mgy. But delta U, the change in potential, would be mg delta y. Make sure that you understand that it's delta U that shows up in the work energy equation, not U. And in fact, U is kind of doesn't mean anything because you could define where y is equal to 0 anywhere you want, and the thing should still work. Up here also, if I let this as just a differential, I could say du is negative f dot dr, and f dot dr is going to be fr, the f component of that, in the dr direction, negative. So now if I solve this for fr, I get fr is negative du dr. So that's kind of relates to this. I can find the potential from the force, and I can find the force from the potential by taking the derivative, if I know that way. So there's a couple other potentials. I'm not going to derive these here. I will derive these later. If I have F equals 0, negative mg, that's not a vector, 0, then I get a delta U is mg delta y. If I have F equals negative g m1 m2 r hat over r squared, then I can solve this as a potential, and I get U is negative g m1 m2 over r. Notice that these are different, right? One, this is a vector. The force is a vector. This is a scalar. Also notice this depends on r. This depends on r squared. Okay. There is a negative sign there, and that is important because we want this potential to be to go to 0 as r goes to infinity, and we want it to be negative so that it's an attractive force. Negative means attractive. If I go the other way, I feel like I'm blowing through stuff here really quick, but that's fine. We also have the Coulomb force gives us the Coulomb potential. U electric is 1 over 4 pi epsilon naught, Q1, Q2 over R. Notice there's no negative sign here. There is a negative sign there because here I could have a positive or negative charge, Q2. So it could be attractive or repulsive. Either way is fine. Okay, let's go over some important final words. Path independence. I didn't really talk about that. Independence. So you can only make a force into a potential if the work done does not depend on path. So if I go from A to B, and I go this way, and I take this path, and it gives me the same work, then it could be path independent. You actually have to show every single path is the same. But any path should be the same. And if it only depends on the starting and initial positions, then I can make it a potential. What about friction? Work done by friction. Well, the work done by friction is complicated anyway. But we can't make this a potential because if I push a block this way, and then I push it this way, then since it's moving along a longer path, and friction's always in the opposite direction of motion, this is going to be more work. So the path does matter. So it's not path independent, so no U. Why do we do energy anyway? Well, it turns out that by only looking at changes in position, we can solve some problems that would be very difficult to solve with other ways. One of the ones we're going to do, and I'm going to do this later, is, what if I drop a rock really high and I let it fall down? If I wanted to use the momentum principle, I have a non-constant force. That non-constant force is really difficult to deal with over this whole time interval. But if I use work energy, I can use my gravitational potential energy, and I can do that. I don't really care what happens in the middle. I can just solve it that way. Now, let's look at the work energy principle. work equals F dot delta R, change in energy. And that could be any kind. And then the momentum principle, which I'll write as F dt equals delta P, right? I can multiply both sides by delta T. So they both deal with forces. If the energy depends on velocity, they both depend on mass and velocity. But this depends on a displacement. This depends on a time interval. This is a scalar equation. This is a vector equation. So they look very similar, but they're quite different. And that's a 40-minute video, and I'm just going to stop there because I've gone way too long, and I'm getting a little tired of this. But that is a long chapter. Okay, so we're going to have to do a lot of practice problems on here. I'm going to go ahead and make a video deriving this because I think that's fun. And I'm also going to talk about things like escape velocity. Definitely need to talk about those. And then we'll do a whole bunch of practice problems. But I'll post those at some point. Okay, read the book. It's awesome.